This paper is entitled Toward Chromium Speciation in Water Samples. It's critical to mention that the samples are water and nothing else, because different approaches would have to be applied for different types of samples, for example, solid samples. So we're going to deal with water samples using functionalized graphene oxide and a portable microplasma on a plastic substrate. My name is Vassili Karanassios. My co-author is a former student of mine, Daniel Cebula. I am a professor in the Department of Chemistry at the University of Waterloo, and I'm a co-founder of a degree program in nanotechnology engineering at the University of Waterloo. The paper is presented in IEEE FLAPS conference. It's a virtual conference and is paper 6113, and ideally was supposed to be presented in Manchester, UK on Tuesday, June 22nd. You may ask why chromium and why look at the speciation. The term speciation refers to the oxidation state. Oxidate is oxidation state. For example, we're looking at chromium. So there's chromium 3+, oxidation state 3+, and there is the same chromium but with an oxidation state of 6+. The question is, why are they significant? Well, chromium with an oxidation state of 3+ is an essential micronutrient. Chromium with an oxidation state of 6+ is a reported carcinogenic. Chromium occurs naturally in Earth's crust at about 100 parts per million, and chromium is the 22nd most abundant element. Uses of chromium, chromium plating, it's a stainless steel additive, so there are multiple uses, and let's just say doorknobs and water faucets. In the lab, chromium has as many as 11 oxidation states. In the lake environment, it's chromium 3+ and chromium 6+, but chromium appears as a molecule, whereas here is an ion, chromium 3+, this is a molecule, and this molecule is negatively charged, and we're going to take advantage of this, because in lake environments, in water samples, only those two oxidation states are thermodynamically stable. So if we look at the species that will be present in a lake water, we're going to look at a simplified Pourbaix diagram. It's a diagram that tells us what species are present. This axis here is affinity for electrons versus standard hydrogen electrode, and this is pH. And the dashed lines here is pH, let's just say 6.5 to about 8, because that's the natural pH for lake water samples. Without getting in too much detail here, there's two species that are, you can see here, is chromium 3+ OH2 or chromium 3+ OH2+, so they're positively charged, and there's the chromate, it's negatively charged. So we have molecular species, positively charged, negatively charged. So we can determine one species and then the total by the microplasma. And I will show you how we do that. We're going to use graphene, and we're going to use graphene because both sides of graphene are accessible. So we're going to grab a lot of chromium, so we increase the absorption capacity. But graphene, there are no charges. This is why we have to modify graphene, to functionalize it. So that's one way of functionalizing graphene. So we have a molecule here, negatively charged. We functionalize graphene by putting NH3 groups. So this is an H3+, so they will attract those two species. Alternatively, and I will show you in the next slide how we can do that alternative. Alternatively, we can add carboxylic acids by adjusting the pH. We're going to dissociate the COOH to make it COO-, and then chromium 3+ will be attracted, or any molecular species that's plus, it will be attracted. So if we modify graphene, we can either add positive functionality or negative functionality. And by doing electrostatics, we can adjust the pH, and doing electrostatics, we can attract the appropriate species. Now, in reality, we're going to take a solution sample. We're going to determine the total concentration of chromium, that is to say, both oxidation states, and then by difference, we can determine either chromium 3 plus or chromium 6 plus. So, as a concept then, we're going to have a miniaturized plasma. We call it MPD, or a microplasma. This is a facsimile or a cartoon version of the microplasma. This could be, the depth could be 150 micron. The width of a typical human hair would be about 100 micron, the diameter of a typical human hair. It could be as much as maybe a bit less than a millimeter, 900 micron. The length, it would be maybe an inch, maybe more. So the sample will come in through here. We're going to apply electrical power from a battery. We're going to convert the DC from a battery into AC, and we're going to strike a microplasma, and we're going to bring the sample through here. Now, I want to emphasize that the gas flow rate here is in the milliliter per minute range. This is compared to and contrasted with a typical inductively coupled plasma. An inductively coupled plasma is another plasma that is probably the most widely used plasma for chemical analysis. Unlike the battery operation here, the typical ICP uses radio frequency, let's just say 27 megahertz, but 1 to 2 kilowatt of electrical power. So really it cannot be used out in the field, and there's about an aggregate or a total of about 20 liters per minute. For the large plasma, the typical microplasma, it would be in the milliliters per minute. So we have low electrical power, battery operation, and we have low flow rate. So the typical plasma torch then, this is the plasma torch, this is the plasma. The sample comes in from the bottom, and you can see it here, the yellow is supposed to be the sample, and the torch, the diameter of the torch is about 2 centimeters. The length of the torch is about 20 centimeters. So we want to go from liters per minute, as is with a typical ICP. These inductively coupled plasmas are widely used in environmental analysis laboratories. There are probably more than 100,000 systems in use worldwide. The typical cost will be $100,000 or more, depending on how many accessories one equips their ICP. So you go from hundreds of thousands to relatively inexpensive. In fact, we have microplasmas that we 3D printed. And we go from kilowatt of power to watt of power. So for gas flow rate, from liters per minute to ml per minute here, and from kilowatt that we have here to watt here. So we can make them portable. And this is the what we call the take the part of the lab to the sample kind of application. So in terms of an ICP, the typical size here, to remind you, about 20 millimeters. The size of a quarter, an American, Canadian quarter, are the same. About 60 millimeters is the height here shown in this figure. So the sample comes in from the bottom, and the microplasmas that we've designed, now they take, instead of 1.2 kilowatt, take 5 watt of power, and this is 0.5 millimeter, 1 millimeter by 500 micron. So this is the depth in this particular case is 500 micron. So this is our microplasma. So we're going from something that is big as this to something that's as small as this. So over the years, we've designed a number of microplasma around millifluidic channels. This is a microplasma. There's one electrode here, another electrode here. The sample comes in through here. The microplasma is sufficiently small, so it fits inside the letter A of the 1-cent coin. This microplasma is 3D printed, so that we don't have to fabricate it using semiconductor fabrication technology, we can 3D print it. So this microplasma costs less than $10 to print it. Again, here's one electrode, here's another electrode. We apply electrical power between those two electrodes. The sample comes in through here, and it's called the microplasma because it fits inside the letter A of the 1-cent coin. As I said, we have microplasmas that are the size of a postage stamp. And this is the same microplasma here. The coin is used for size, is the size a bit smaller than an actual sugar cube. So this is a sugar cube. This is a bit smaller than the sugar cube. And in this particular case, the sample comes in through here. The microplasma gets formed between these two electrodes. So we used a variety of substrates and different fabrication technologies that we've experimented with. This is an experimental setup, a typical experimental setup. These are battery operated. So this is DC, this is an AC converter, and this is the microplasma here. It's a fiber optic cable, goes all the way around into a portable spectrometer. We see here that we have goggle safety glasses for size more than anything else. And we don't have to use a large computer or a desktop as shown here. We can run this, and we published it, we can run it using a smartphone. So this is an example now. We run 1 ppm, 10 microliters of chromium standard. So this is intensity, this is wavelength, and this axis here is time. So this is about 1 second total. These are the chromium spectral lines. We can subtract the background, so that's the background. We can subtract the background, so that would be the chromium signal subtracted. So this is the background, that's around 0 now, because we subtracted the background. This is time, and these are the various chromium spectral lines, and there's probably a little bit of sodium here. And then, if we look at if we add them all up, if we add all the spectra or the spectral episodes that contain chromium signals, this is what we see. So this will be intensity. This is versus wavelength. We have a bit of overlaps here, but we have really nice separation for the spectral lines, and this would be the spectral lines. So we can use any of the spectral lines. This is actually a triplet, and this is actually a doublet, and we identify those using another spectrometer. But at any rate, we can use this for the, analytical determination and for construction of calibration curves. So now we have further miniaturized the microplasma. So this is our microplasma here. This is a polymeric substrate, you can see. We have experimented with helium hydrogen as the carrier gas, the gas that goes through the needle through here, or argon hydrogen. Hydrogen is 3%. This here is about less than 200 micron, let's just say, and we have a polymeric substrate. The reason why we did the polymeric substrate is to make everything cheaper and do not use a lot of time to construct the microplasma. So in conclusion then, we can determine the total chromium concentration. So this is chromium total in lake waters by battery operated microplasma. It is possible to determine chromium-3 various oxidation states such as chromium-3 plus and chromium-6 plus using modified graphene oxide or functionalized graphene oxide and electrostatic approaches the way I've described earlier on. And work in this area is in progress. Hopefully within the next little while we'll have really data that will describe this whole process the way it was done, and we can publish it. Thank you for your attention, and I would be happy to answer any questions you may have.